Good morning, everyone. My name is Abhishek, and today I'm going to talk about what drives the ocean's supercellular circulation. And I have done this work mostly with Jan Jika and Katia Dominguez. And some of you already seen this talk I presented in the last month, the MOM meeting, but I have added some new stuff in today's talk. So as you can see, this is shows the spread in the projected sea level change among the climate models participated in the CME 5. And you can see here the spread is largest in the high latitudes in both hemisphere and also in the North Atlantic and Northwest Pacific. And Coolbrot and Gregory suggested that this spread exists due to differences in the ocean heat uptake and also the vertical heat transport among the climate models. To understand the mechanisms of the vertical heat transport, we use the budget approach, which is mathematically written here. So this term represents the total heat tendency, and this term represents the convergence of heat due to advection or the convergence of pressure. Here, pressure I choose as a temperature. And the second and third term represent the convergence of heat due to subgrid scale processes, which mostly parameterize in 1 degree model. And last term represent source and sink. This term is again the sum of the resolved advection and parameterized meso and sum meso scale advection due to eddies. And this is eddy diffusion. And this term is the direct signal diffusion, KPP convection, and sigma diffusion. And F is the source and sink term is the surface fluxes. It includes the radiator and turbulent fluxes, short wave penetration, precipitation minus evaporation, river runoff, and fragile. In recent, Dias et al. Has done a comprehensive analysis in which the study investigated the individual role of all the terms listed here. This study also explored the role of the superresidual transport, which is defined as the sum of the dissolved advection, mesoscale advection plus mesoscale diffusion, and concluded that the superresidual transport shown in the red dashed line here transport heat downward in the upper ocean, which erode newly formed water masses, and in the interior ocean, it transport heat upward, which cools the deep ocean and further balanced by the diagonal diffusion. But the main limitation of this study and also the budget approach, you cannot separate different part of the ocean circulation. Like for example, how much heat transport by the meridional overturning circulation or how much heat transport by the Antarctica bottom water circulation. To do that, the Giga et al. 2015 projected a three-dimensional circulation in depth and temperature coordinate by using the steam function, as you can see here, and found three main cells. So as you can see here, the red cell, which is transporting warm water downward and cold water upward, and this cell is mechanically driven or wind driven, and this cell is connected with the interhemispheric overturning circulation. And in the cold cell, which transport warm water upward and cold water downward, and it is buoyancy driven, and this cell is connected with Antarctica bottom water circulation. And there are two cells in the above 500 meter in warmer temperature, which shows the tropical and subtropical gyre. This study also investigates how much heat transport by the individual cell, as you can see in the right figure, shown in the red line. So the red cell transport heat downward in the ocean and warm the ocean, whereas the cool cell transport heat upward and cool the ocean and further balanced by the diabatic processes. So I'm really interested or going to show what process drive the individual cells. So the main objective of this talk is to quantify the contribution of different components of ocean circulation to vertical heat transport, quantify what physical processes drive different components of the ocean circulation and their associated heat transport. And first time we define the superresidual circulation in temperature and in depth coordinate. So the top left figure shows the residual circulation. I calculated similar way as in Giga et al. In excess OM, and we can see here the excess OM also capture or produce the same cold and warm cell. So here the warm cell again showing the warm water is going down and cold water is coming up, and cold cell is showing the warm water is coming up and cold water is going down. So we define our diathermal circulation, in which we combine the loop net tendency with advective tendencies. We have first time used the tendencies to calculate the diathermal circulation. As you can see here, so diathermal circulation qualitatively showing the similar circulation as we find in using the vertical velocity, and it's the red color here showing the warm water is going toward the cold water, toward the colder, move toward the colder temperature, and the cold cell is showing the cold temperature moving toward the cold water moving toward the warmer water. And this diathermal circulation is showing the contribution from the kinematic process or the advective process to diathermal circulation. But if you sum in the same way all the non-advective processes or the diabatic processes, you will get equivalent opposite circulation as a diathermal circulation. So by using this function, you can quantify the contribution from kinematic process to diathermal circulation and also thermodynamic process to diathermal circulation. We further look the individual contribution to diathermal circulation, and you can see here the mean circulation in the warmer temperature greater than 0 is mostly warm the ocean, which is further balanced by the mesoscale eddies and some mesoscale eddies. But if you see in the colder temperature, the cold cell is showing here in above 1000 meter. This is supported by mesoscale circulation and some mesoscale. But the local tendency or the net tendency has very small contribution to diathermal circulation in the warmer temperature. Warm I mean like 3 degrees centigrade. But in temperature between 1 and 2, there's small like approximate 2 C2 contribution to diathermal circulation, and it could be a model drift. And on the right figure showing the thermodynamic contribution to diathermal circulation, and we can see here the dia-mixing and ISO has largest contribution, where the diapinal mixing transport heat or water from warm to cold and from surface to deep ocean, and it's compensated mostly in temperature greater than 0 degrees centigrade by isopycnal mixing, which cool the ocean. But interestingly, if you see in temperature less than 0 degrees centigrade, isopycnal mixing warm the ocean. So isopycnal mixing has a negative contribution to negative role to ocean to cool the ocean, but in the negative temperature, it has positive feedback which warm the ocean. And KPP and ice and convection is important, and convection is also cool the ocean and it's really important in temperature less than 0 degrees centigrade and mostly work up to surface to 2000 meter depth. So I further see, so this is the circulation view, but I further investigated how much heat transport by the total diathermal circulation and what process drive to individual circulation cells. So the top left figure shows the heat transport by the diathermal circulation. As you can see in the black line, so diathermal circulation transport heat downward up to 2000 meter, and in the interior it transport upward, which is further balanced by the isopycnal mixing. And the conclusion of this is repair the global budget and will agree with the previous finding in Tyres et al. And also Jika et al. And when I further split into the cold cell, which is shown in the left bottom figure. So cold cell, which represent the Antarctica bottom water, transport heat upward throughout the water column, which is balanced in the upper 1000 meter by the isopycnal mixing, and in the deep ocean by the diapycnal mixing. And convection has a secondary role to cool the ocean in temperature less than 2 degrees centigrade. And the right top figure shows the warm cell, so that's shown here. So warm cell transport heat downward in the upper 2000 meter, which is further balanced by the isopycnal mixing, and the surface shell, which is mostly in the upper 100 meter and transport large amount of heat, which the surface shell shown here transport 1.2 petawatt heat at 50 meter depth from subsurface to surface, and further balanced by the convection and diapycnal diffusion. So I further I mentioned in my second slide about the superresidual transport, but here we first time define the superresidual circulation in temperature and depth coordinate. So the first figure showed by using the previous definition, in which we haven't included the some mesoscale advection, And the middle panel shows the superficial circulation when we include the submeso scale advection. So what we found, so the SRC or superficial circulation is dominated by thermally direct cell. Thermally direct, I mean the cold cell, and it transport, if you see at the 1000 meter depth, it transport approximate 15 centigrade of water downward, which is for at 0 degree centigrade, and it further warm by the diabatic process at 2 degrees centigrade before it upwell at the surface. And if you see the heat transport by these two definitions, so I here mostly the blue color is showing the when I include the submeso scale advection. So superficial circulation transport heat upward throughout the column, which further balanced by the diaphragmal or diabatic process. So it's really showing the monk classical advective diffusive balance. I further look the superficial circulation in different resolution in axis. So the top figure shows the axis 1 degree, in which we parameterize meso and submeso scale at each, and the bottom and the middle. This figure shows in quarter degree, which is partially resolved at each and partially parameterized by meso scale. And the third, this figure shows the 10th degree model. There is no parameterization for the meso scale at D. And we can see all three configurations dominated by the cold cell. So all three configurations capturing this cold cell, but the 1 degree and quarter degree had two thermally indirect cell. Indirect means red cell in colder temperature, which is not present in axis 10th degree model. And also, if you look the upper 1000 meter, in all three are like they are showing the cold and warm cell. So and also if you see here the heat transport by each configuration, heat shown in the bottom figure. So SRC or superficial circulation transport heat in 10th degree is 3 times larger if you just consider particular 1000 meter depth than the quarter degree and the 1 degree. It seems like the advection or superficial circulation in 10th degree model is much larger. It's cool ocean more than the 1 and quarter degree. So on conclusion, so using the advective tendencies, we have presented the diathermal circulation in temperature and depth coordinate, which exactly describe contribution to vertical heat transport. We have revealed the diathermal circulation and the role of the different diabatic process in its individual overturning circulation cells. For the first time, we have introduced the superficial circulation in depth and temperature coordinate. And the SRC or the superficial circulation dominated by thermally direct cell with cold water sinking and warm water upwelling, consistent with the classical description of the deep ocean circulation. And the axis OM2 1 degree quarter and 10th degree looks qualitatively similar, although 10th degree does not capture the warm cell in temperature, in the negative temperature in subsurface. So SRC or the SRC allow a direct comparison between models with different resolution in different partition between resolved and parameter, and could be a good diagnostic for the model to compare the high resolution model with the low resolution model. And thank you.